How solar panels are made in factories. Manufacturing in the solar industry refers to the process of producing goods and components at every stage of the solar supply chain. Even though some concentrating solar thermal manufacturing does take place in the United States, the vast majority of solar manufacturing is associated with photovoltaic PV systems. All of the components that make up these systems, including the photovoltaic modules, the racking and wiring, the power electronics, and the system monitoring devices are made. Manufacturing of PV modules, silicon-based PV. Crystalline silicon is used as the absorber material in the vast majority of PV modules that are available for commercial purchase. These modules require several distinct manufacturing stages that are normally carried out in isolation from one another. Polysilicon manufacturing. Polysilicon is a high-purity, fine-grained crystalline silicon product that, depending on the technique of manufacturing, can typically take the form of rods or beads. Polysilicon is used in a wide variety of electronic applications. Metallurgical-grade silicon, which can be derived from quartz sand, hydrogen, and chlorine, are the primary ingredients required for the synthesis of polysilicon, which is then often produced using processes that rely on highly reactive gases. The silicon-hydrogen-chlorine combination gas is passed over a heated silicon filament in one method known as the Siemens method. This method breaks the chemical bonds and deposits the silicon atom on the filament, which ultimately grows into a huge U-shaped polysilicon rod. In a process that repeats itself, both hydrogen and chlorine atoms are recycled. The high-purity polymer and the filament itself are both manufactured of pure silicon, so that the filament does not introduce any impurities into the polymer. Small beads made of silicon are placed at the base of a vessel in the shape of an upside-down cone. A gas mixture consisting of silicon and hydrogen is then pumped into the vessel, which causes the small beads to rise to the surface and float near it. Because of the heating of the vessel, the bonds between silicon and hydrogen are broken, which leads to the silicon atoms depositing onto the little beads until they become too heavy to float and so sink to the bottom of the vessel, where they may be harvested and prepared for use. The production of ingots and wafers begins with the placement of polysilicon in a container that is then heated until the polysilicon transforms into a liquid mass. This allows the polysilicon to be molded into wafers. One method for growing monocrystalline silicon is known as the Czochralski process. In this method, a big cylindrical ingot of monocrystalline silicon is developed by gently placing a small crystalline seed on the surface of the liquid and then gradually dragging it higher. In a different method referred to as directional solidification, the liquid mass is gradually cooled until it begins to solidify from the bottom up, which results in the formation of a large-grained multicrystalline silicon ingot. After that, diamond-coated wire saws are used to slice the silicon ingots into wafers of extremely fine thickness. The term kerf refers to the silicon sawdust that is produced during the process. A kerfless wafer can be produced in one of two ways, either by plucking cooled layers off of a molten bath of silicon or by utilizing gaseous silicon compounds to deposit a thin layer of silicon atoms onto a crystalline template in the shape of a wafer. Kerfless wafer manufacture is less common, but it is still possible. The next step is called cell fabrication, and it involves turning silicon wafers into solar cells. The initial process involves the removal of saw marks from the surface of the wafer and the enhancement of the amount of light that is absorbed by the wafer when it is subjected to natural light. The subsequent processes are very different from one another depending on the architecture of the device. The vast majority of cell types necessitate exposing the wafer to a gas that contains an electrically active dopant, as well as coating the surfaces of the wafer with layers that enhance the performance of the cell. Screen printing of silver metallization for use as electrical connections is another practice that is extremely widespread throughout cell types. In a facility that specializes in module assembly, a procedure known as tabbing and stringing is used to connect the silver busbars on the front surface of one cell to the silver busbars on the rear surface of a neighboring cell. This connection is made using copper ribbons that have been plated with solder. On a sheet of glass that has been covered with a sheet of polymer encapsulant, the interconnected set of cells has been arranged with the faces down. After the face-down cells have been covered with a second film of the encapsulant, a resilient polymer backsheet or an additional piece of glass is then placed on top of them. After being laminated in an oven to make the module watertight, the entire stack of materials is subsequently fitted with an aluminum frame, edge sealant, and a junction box in which the ribbons are connected to diodes that prohibit any backward passage of electricity. The current that is produced by the module is transported via electrical wires coming from the junction box to either an adjacent module or the power electronics of the system. PV using thin film. The term thin film PV may be used to refer to a variety of various absorber materials. However, cadmium telluride, CT, is the most prevalent of them. Modules made from thin-film photovoltaics are normally processed as a single unit from the beginning to the end, with each step taking place in the same location. In most cases, the production procedure begins with float glass that has been covered with a transparent conductive layer. Next, the photovoltaic absorber material is deposited onto the float glass using a technique known as close-space sublimation. The employment of a laser allows for the patterning of cell strips, as well as the formation of an interconnect pathway between cells that are near to one another. The stack is laminated, copper ribbons are adhered to it, an encapsulant sheet and a second sheet of glass are placed on top of it, and then it is made waterproof by being laminated. At long last, a junction box is fastened to the module's bottom rear side. In this location, the electrical cables of the module are connected to the copper ribbons, which are then routed into the junction box via the holes in the rear glass. Various racking methods. Racking systems are the common name given to the structures that are designed to hold photovoltaic modules in place, whether they are installed on a roof or in an open field. There is a substantial amount of variation in the production of photovoltaic racking systems that is caused by the location of the installation. Steel, which is usually coated or galvanized to protect it from corrosion, is used in the construction of ground-mounted racking, which necessitates the use of concrete foundations. Large ground-mounted systems often make use of a technology known as one-axis tracking, which assists solar panels in monitoring the sun as it travels from east to west. To track, you need mechanical components such as motors and bearings. There is also the option of using stationary racking, which is more often known as fixed tilt. The kind of roof must be considered while installing roof-mounted racking. Steel racking with a fixed tilt is typically utilized on flat roofs, such as those seen on big commercial or industrial structures. Electronics of power supply. Electronic components, such as power optimizers and inverters, are constructed on printed circuit boards for use in photovoltaic modules. Direct current DC power, which is what is produced by a solar panel, is changed into alternating current AC electricity, which is what is used by the electrical grid. This hardware does this conversion. Gain a better understanding of the operation of inverters. The circuit board template is the first step in the assembly process. Using robotics, small components such as transistors and diodes are positioned, and then a solder paste pattern is printed over those areas. When working with larger components like as capacitors and transformers, it is sometimes necessary to arrange them by hand on the board. After all of the components have been attached to the board, it is moved through a solder bath inside a furnace so that the components can be connected. The entire circuit board has a lacquer coating and is encased in a casing that is sealed against water and has ports for external connections. So this is the end of our today's video. Do you like it? Kindly give your valuable response in our comment section below, and don't forget to subscribe to our YouTube channel for more interesting and informative videos.